Good afternoon, everybody. Flyers, welcome back, and welcome to the general public. It's my pleasure to kick off session 1, 2, 3, 4, I believe, of the Association of Space Explorers 32nd Planetary Congress. I want to thank Space Center Houston for hosting us, obviously, but I also like to thank Jacobs for having provided us with a lovely lunch and also for sponsoring this session. With that, I'll turn it directly over to my friend Dan Hartman, who is the relatively newly minted program manager for the Gateway, to introduce the session. Thanks, Dan.
Thank you, Ellie. That's for you. Let's see, good afternoon and welcome to the Association of Space Explorers Forward to the Moon panel. As Ellie mentioned, I'm Dan Hartman, and together with Christian, we will be leading and moderating this panel. Joining us on stage is Alexander Gerst from the European Space Agency, Koichi Wakata of JAXA, and Jeremy Hansen of CSA. Initially, Ken Bowersox was supposed to be here. He's sorry he can't participate today. He is actually supporting the administrator in a hearing tomorrow. So, and coincidentally enough, that hearing is on the NASA proposal to land on the moon in 2024 and give an overall status of where we are. So he can't join us. In addition, we had Sergei Krikalev on our panel. And as you know, he'll be attending the funeral of cosmonaut Alexei Leonov, who was the first human to ever conduct a spacewalk, who recently passed away. So he'll be attending the funeral. And he sends his regrets as well that he can't join us today. The presentations you'll hear this afternoon will discuss kind of all of our plans as we go forward, NASA, ESA, JAXA, and CSA's exploration plans and activities. I can tell you significant progress has been made across the international community over the past couple years. Quite honestly, taking the partnerships that we have under the International Space Station and broadening those to the cislunar and the moon surface journeys that we're getting ready to undertake. So these are very, very exciting times for our countries. And each country presently is looking to get funding approved through their governments, and that is picking up on a very brisk pace. And a lot of ministerial conferences coming up here within the next month or so. So we're really looking forward to that. Let's see, each one of us will give a presentation of kind of our agency's status. And then I'd ask, there'll be a quick 5-minute question and answer period after each one of our presentations, and then we'll open it up at the end as well. So now I'd like to introduce Christian Feichtinger, the co-chair of this session. Dr. Feichtinger took up the post of the International Astronautic Federation Executive Directorship in January of 2012. He spent 3 years as a senior advisor on exploration at ESA, and before then was the head of ESA's permanent mission in the Russian Federation after working as the agency's representative for human spaceflight in Moscow for 10 years. Christian was also a flight operations support manager for Euromir 94 and 95 in the control center outside of Moscow, and he holds a PhD in space experimentation from Graz University of Technology in Austria. So, Christian?
Well, good afternoon, ladies and gentlemen. It's a great pleasure and an honor for me to be here and to have the opportunity to co-chair this distinguished session. Let me just mention that the connection between the partnership between the Association of Space Explorers and the International Astronautical Federation is a very, very fruitful one. Since many years, the Association of Space Explorers is a very distinguished member of our federation, and we have a partnership to co-chair sessions here at the congresses of the ASE. And we are also hosting astronauts events organized by the association at our International Astronautical Congress, which, by the way, will take place next week in Washington, D.C. And you all may have heard the theme of this Congress, Space, the Power of the Past, the Promise for the Future. And that's actually what we're all talking about here. So whoever has not yet planned to come to Washington next week, please be invited, be our guest there. We would love to see you there. Now, without further ado, I would like to introduce Dan as not only our chair, but also as one of our distinguished speakers here. With nearly 25 years of NASA service, Dan was assigned the role of NASA Gateway Program Manager, assuming responsibilities in February 2019. Prior to this assignment, he was the ISS Deputy Program Manager for 4 years, ensuring safe operations of the ISS while enhancing research throughout the research throughput and ushering in new commercial entities. I think with glasses is better. Dan has vast experience in managing large complex spacecraft, servicing as the Mission Management Team Chair, the ISS Vehicle Office, and the ISS Transportation Office, integrating commercial cargo and commercial crew with the ISS. He's a graduate of Texas A&M University with a Bachelor of Science degree in Electrical Engineering. It's my great pleasure to give the floor to Dan now for his presentation.
Thank you, Christian. Let's see, Gateway. Gateway's been kind of under discussion for 2 or 3 years. And then we finally kind of culminated that in what we call a formulation sync review in February of this year. And at the same time, following that, we stood up a very, very small Gateway program office of about 25 folks. And so we're trying to run this program a little differently. Obviously, we use a lot of industry and a lot of our institution civil servants, but the overall Gateway size, like I said, we kind of challenged ourselves. We had the opportunity to select many of our teammates of the 25 directly from the pool at JSC, and it's turned out to be a pretty strong and incredible team. And so we're all very passionate, all very dedicated to try to pull this thing off, especially given the mandate that we have in 2024. So we have been busy working on, you can imagine, requirement sets, procurements, getting things in motion as we try to progress toward the 2024 mandate. So we have been moving fast. On a path of kind of landing on the moon in the 28 time period, based on the SPD-1. But then in March of this year, again, I started in February. In March of this year, the vice president, they'll check out their system, check out the ECLIS system, check out the power of the propulsion systems before doing the TLI burn and getting yourself on the way to the moon. Can't tell you the specific orbit that they plan to, obviously.
Still on the Gateway. So we're looking for several hundreds of them, of course, for ISS, but already quite a few in preparation for Gateway and Moon. One of the main elements that ESA is providing already to the Gateway to going forward to the Moon, that is the Orion service module. It's based on the technology of the European automated itself. And so it's continuing its life as the service module about it before is the first time of the Gateway. It's designed to, we can already contribute at that stage in addition to the service modules of Orion, and that is actually something preparing for the next stage of the Gateway, as Dan talked about it. The capability of refueling the Gateway, the power and propulsion element. So in order to do that, we want to contribute a module that does that. We need the fluid lines, and the interface is already prepared for that. So that is going to go onto the Halo in the phase 1 in anticipation of what comes next. Then we are contributing the communications equipment between the power and propulsion element, or the Halo, and the Moon surface. The NASA is providing the Earth communications, ESA in this case providing Moon communications, and also as a backup for Earth communications if a problem should arise. And we're looking into already putting a few scientific experiments onto phase 1. But really the time when the Gateway will sort of thrive as a outpost, as a fully fledged research outpost of humanity in deep space, and basically in a different world, that's phase 2. And that is when really the main elements of ESA contributions will fly to the gateway. In this case, it's, well, I'll get to it in more detail. You can just see it on this slide here, which I think is actually pretty exciting because you might be looking at really one of the first more accurate drawings of the gateway. It's not just something that comes out of the PR division of somebody drawing a nice like space station as artist's depiction. This is really how the gateway could look like. So look closely at this slide. You might see it in the future again. So to me, that's pretty exciting. So the ESA elements that we want to be contributing, I've shown in red, which is in the top middle is the Esprit refueling module that is there to refuel the power and propulsion element to provide continued well, navigation capabilities and to allow the gateway to stay on its track around the moon. Then we want to contribute the International Habitation Module, the IHAB, together with international partners to extend the capabilities of crew actually living on the gateway. So the IHAB is basically a standard sort of module as we already delivered it to ISS. It's going to be the second pressurized permanent module on the gateway. It's pretty much the first module that allows to do science. It has several docking ports. JAXA is planning to contribute the life support system. We're looking forward to that. CSA is providing the robotics interfaces of the gateway of this module on the outside, and we're planning to have a part of the life support also an exercise device in there, waste management system, crew quarters, and we're targeting a launch on either SLS or a commercial vehicle. So the other one I talked about is the refueling element. It's not only there for refueling, but also part of it is the communications equipment for the moon, as I talked about it before. It might have a science airlock, which is really interesting. It might not be in that module, but it might be combined with the Russian airlock coming up there, and allowing us to even launch like little satellites in that orbit around the moon. So CubeSats, for example, which of course will be very interesting. Also very interesting for my colleagues who are about to fly on the gateway. They're probably going to look forward to that module. If we manage to get that through, then it will have some really nice windows. One of the important things. Thanks, Conrad. I know you appreciate that one. Just adding it up, what are the lunar elements? The way forward to the moon with ESA. The first three of these I already talked about. I just want to add that these elements that we talked about that we want to contribute, the Esprit and the IHAB, we want to actually also operate them from Europe. We don't need an own control center for that, but we sort of have a part-time control center that if there's operations, for example, refueling, that this is actually run end-to-end from Europe. We're also looking into a transfer vehicle, a cislunar transfer vehicle, right now only as a study in this proposal, but the technology would also be based on the service module. This would be a vehicle that could bring cargo from Earth to the gateway and back, and that's also very interesting, it could also move an ascent and descent stage from the gateway to a lower lunar orbit and back, so that would already address the question regarding reusability. That would be really the next step towards that, because that vehicle could do that many times. We have right now a few missions of opportunities that we're running just for technology development. We have Lunar 27, that's a Russian probe that's going to land on the moon, and we have 2 payloads on there that look for precision landing and also for surface operations, surface investigations. The prospect will actually drill into the lunar soil. We're also looking at a large logistics lander, EL3, in a study that's in the class of 1.5 to 2 tons, so in between the smaller landers that are in plan now, and but smaller than the big landers who would land the human system. So it's something in between will also probably come in very useful. Also, we have a few commercial providers looking into things like providing services like communications around the moon and navigation. So we don't have a GPS or a Galileo system yet around the moon. So it's actually it's a major problem to navigate there, to communicate there, and that's something that we think commercial providers could build up. And last but not least, we're having looking into payloads for in situ space resource utilization. And what we have in mind there is a payload that can actually extract oxygen end to end from lunar regolith. That's also being studied right now and in the plan for the next program proposal. So in addition to those elements of hardware that we want to send into space, we also support training and technology development on Earth. We have this new facility called Luna that we're hopefully starting to build in the next months around EAC, which is basically a moon simulator with like a regolith surface inside, allowing for technology testing, crew training. We have a hab that we want to sort of build, integrate in there. And lots of sort of artificial intelligence systems, VR environments that allow the testing of the technologies that we will need on the moon. And of course, partners are welcome. We have already lots of interest from around the world, partner agencies to test their equipment there before they send it up. Also, what we do in terms of crew training, we have a few analog trainings that were developed in the last years. I see several of my colleagues who've participated in some of these. These are Pangaea caves, or on the US side, Nemo or Ansbet. This is a photo that I actually took 2 weeks ago in a Slovenian cave. Or we were on that photo. Actually, we were 6 days in a cave, and there was an amazing analog to doing science in a very hostile environment where it's tricky to live and work, but still you have to do science. So it's actually one of the best analogs that I've seen to being in space. So I would like to finish up this presentation with 2 photos that I've actually taken from the ISS, just as a reminder of, how close Moon is. It's really only 3 days out. It's as long as, even in a small European country, a few hundred years back, that's how long it took on a horse cart to cross that country. Nowadays, that's how quickly we can get to the Moon, and I think that is, something that should tell us we're ready to go. So thank you.
Thanks a lot, Alex, for giving us this insight in the European plans for participating in this project. I think we have some time for some questions. Do we have a microphone here? We have a question here.
Is it on now? Yeah. Thank you so much for sharing ESA's plans. And ESA's plans beyond low Earth orbit with humans, do you have any new ways you're looking at it, partnering with commercial entities to better engage them in the process to get their real ownership beyond just simple contracts?
Yeah, that's actually a part of that. I briefly mentioned it. I didn't go into too much detail, but we are indeed looking at services that could either do communications around the Moon, relays, navigation system around the Moon, or even transport systems. But right now, we don't have a big provider who's ready to go. So we want to engage them more, of course, but right now, they're just not there yet in Europe. One thing that we also do is, in terms of ISS commercialization, we have, for example, a new platform on Columbus that will be installed, the Bartolomeo platform, that will allow, it's actually a commercial platform already, where a commercial provider will use that to provide space for payloads, science or technology payloads on Columbus. That's already one step towards commercialization.
Any more question to Alex? Yeah, there's one more up there.
Thanks, Alex. You mentioned the ministerial coming up. I wasn't clear on how much of the program has been approved by ESA, and what do you hope to accomplish at this ministerial in terms of moving towards some of those things that you had on your wish list up there?
Yeah, that's a good question. That's always, for ESA, the tricky one, right? I mean, it's a program that really we discussed with the member states, so it's not going to come as a new idea to them. They're all supporting it. The question is right now is how much money do we get together? How much money can we throw in the ring to support that program? So the support is there in terms of programs, and of course with ESA, it's always a thing. Also, you have to look out for who can contribute what. Like you want to distribute the industry around the participating states, and it's also an optional program, so it's not going to be all the 22 member states. So really, what we need to accomplish in this ministerial is to get the backing. Not in terms of only saying this is a great thing, but really get the funding to get things going. But we are already working, building that with the member states' knowledge. They're supporting that. There's the invitation for tender is out for the IHAB. So that is really something that's a project on its way. It's not just there waiting until somebody says yes. But eventually, of course, we will need the backing from the member states. I'm positive, you know. It's good to see that there are people out there who have visions, who have a visionary spirit, and who know what's at stake to actually get this project going. I mean, if you think about us not participating in this would be a catastrophe, and I think everybody knows that if there's a big international cooperation based on the ISS, and we need to be part of that, at some stage there will, well, that time will come at some stage, not be an ISS anymore, and we've been benefiting so much from that partnership. And of course, I haven't mentioned right now the service modules. I mean, that's a done deal. We're contributing them. The first one is already here. The second one is being built. The program proposal now is about purchasing ESM 3 and 4, basically supporting Artemis 3 and 4. So we're pretty sure that's going to go ahead. But the problem for us is that these are actually offsetting the ISS costs of ESA. So we use them to pay for the common station operation costs for ISS. So that does, for us, not yet give us a complete participation in the Gateway program.
Let's have two more questions, one here and then up there.
Ernst Messerschmidt of Germany. I have a question now. ESA has a rocket capable of bringing 2 tons to the moon surface. Probably it will be not used anymore for a longer time and replaced by Ariane 6. Is there any plan to use transportation on the way to the Gateway in one or the other way by Europe in general?
Yeah, that's a very good question, Ernst. Actually, I should have mentioned that one as well. So the Ariane 6 is actually in discussion for the transfer vehicle that's in development and for the European Large Logistics Lander. So if those go ahead, they will be designed to launch on Ariane. Also because so it's important for Europe to have one area where we can have full autonomy, and in that case that would be a project that we could do fully autonomous to contribute to the partnership, but to show that we can do it end to end ourselves. The gateway elements, the IHAB and Esprit, they're not considered for Ariane launch simply because that's an additional service. That's actually, you know, I mean, a launch is an expensive thing. So right now, the contribution that we suggested to the member states and that they agreed to so far is those the gateway modules, Esprit and IHAB. But that does not include an own launch yet. So we're working with our partners to launch it either on a commercial vehicle, or it could also launch on an SMS within Orion and fly to the gateway with those.
One last question, please.
Looking at the most recent successful test for the European Space Service module's main engines, what are the next steps for integrating that into the Artemis program?
Oh wow, that's a question that's for me really tricky to answer because that's already on such a technical level that I'm not too much into detail on that one. Andy is here. Do you know anything more about that one? No, okay. But I mean, it's a really good question. I just don't want to give you, and I could give you like an approximate answer, but I don't want to sort of set you off with something wrong there. But it's right now it's being integrated. I think the two parts have already been put together. Then you. They're going to Brook in a month. Yeah. So can you maybe?
I don't know that specific, but they're going through environmental tests for about the next. Sorry. Environmental tests for. Yeah, they get up there in a month, and I think it's a several months worth of environmental test up there, thermal vac. But I have not heard of that.
So your question is so good that none of the panel nor in the audience could answer it. So go ahead with that one.
Well, thank you for these challenging questions, and let me ask you to join you for another round of applause for Alex.
Thank you.
Now we move on to Japan, to JAXA. It is my distinct pleasure to introduce our next speaker, Koichi Wakata. Koichi was selected as a Japanese astronaut candidate in 1992, qualifying as a mission specialist in 1993. He holds a Bachelor in Aeronautical N2, qualifying as a mission specialist in 1993. He holds a Bachelor in Aeronautical Engineering, a Master's in Applied Mechanics, and a doctorate in Aerospace Engineering. Koichi flew aboard STS-72 in January 1996.
IAH a few hours ago because of that big typhoon that hit Japan. My flight was canceled and I was able to make the first available flight that brought me here this morning. So it's about 5 a.m. in Japan. I'm still trying to stay awake and I finished all my water. And please allow me if I am slow today. Exploration that JAXA has. Okay, great. Our moon mission, mainly, the human exploration that JAXA is now working on. And also, would like to apply to the gateway contribution is habitation technology, basically Eclipse system and a thermal control system. And then other parts of the human habitation capabilities will be applied. And in the HALO mission, HALO module, Habitation and Logistics Outpost, that will be in the early phase of the gateway. We are working with NASA team and the Northrop Grumman team to be able to provide the components such as the thermal control system, pumps, and then maybe batteries. This month we carried US batteries. That is also lithium-ion batteries, lunar surface missions. The other next year, and then after that we are targeting for fiscal year 2021 launch of the first HTVX mission. And with the HTVX derivative, we'll be able to provide next year, maybe, the follow-on crew will arrive on the surface of the motorized rover of dust or samples. And about last week or so, about 2 weeks ago, we deployed the last lander to the surface of the asteroid Ryugu. And this spacecraft, Hayabusa 2, will be leaving asteroid Ryugu at the end of December, around December of this year, and it will come back to the Earth next year, at the end of next year. And then we just want to develop a new system that is only applicable for space. It's very difficult to have wider participation from the industry that has basically nothing to do with space exploration. But even on the surface of the moon or surface of Mars, the gravity level exists 1/6 of a g or 1/3 of a g. And that is very different from zero gravity. So already terrestrial applications could be directly applicable to our exploration missions. So on the moon. So in summary, JAXA will continue to actively participate.
I'm also considering the crews. If they are there for a long period of time, then okay, if they deviate from the solar pole, from the South Pole or North Pole, eventually after X number of days they will have night at the moon. And I think you mentioned in the long run, you might go for 60 or 90 days or something that on the solar surface. And oh, okay, then I'm
Yeah,
entirely, okay. I take my question back.
Okay, is there another question to Jeremy? If not, here. We have one last question and then. I think we need
Should
to
be,
close
should
it.
be an easy one, or a short one at least. My understanding is the original Canadarm did not have automated systems to prevent, say, its elbow from bumping things. That was something manually done, already going to automatically avoid obstacles.
Yeah, and I don't know, and I know Tim's in the audience, he can correct me if I'm wrong. I don't think we actually have on Canadarm2 that ability to automatically protect from the elbow. The way we operationally protect is by constraining one of the joints so that we know, can you guys hear me? So that we know the path the arm will choose to fly. Is that mic working? So if we lock one of the joints, we know the path that the elbow will take, and then we have tested it beforehand, and then we monitor it from the ground, and we have someone in the loop, although there's, maybe there's a couple seconds between pressing stop at the console and it actually stopping. If it's not doing what it's supposed to do, we can stop it from the ground. So what you're talking about is definitely what I'm talking about, is one of the challenges going forward, is ensuring that we can, in blind faith, not have any comm, and when we come back, the operation is complete, and we don't have a hole in the gateway. We won't do it, I promise.
Well, thank you very much, and please give another round of applause to Jeremy. And with that, I would ask Dan to close the session with some closing remarks.
Just real quick. Is that on? Oh, that's right, you told me that. How's that? Is that better? Just real quick, thank you, Koichi, Jeremy, Alexander, for a great panel. Honestly, it's an honor to be on the stage with you guys, and great questions for the team here. Christian, good luck next week at IAC. Thanks for your participation here. Many of us will be there, and so that'll be great. And special thanks to Dr. John David Bartow. He got this panel together. He helped us organize, did all the legwork, so thank you very much, John David. And with that, thank you all for joining us today. It was a great panel. I appreciate it. Appreciate it. Do you want to say anything, Ellen?
Can you hear me? Can you hear me? Can you hear me? Can you hear me? Hello? All right, wonderful. So welcome back, everybody. I am pleased to introduce our last session of the day. It is the next 50 years challenges for future exploration. So in the last panel we discussed, I would call it a sort of near-term plan, but obviously we need some technologies to help get us there, and that's what the session chair, Steve Oswald, is going to tell us about. Take it away.
Okay. Home stretch. So we're going to try to be out of here by 5:30, but Franklin brought a cast of not thousands, but lots. And so we'll see how critical mass. But before we get to Franklin, we've got a couple of other guests, and you know, Sultan and Aramco are sponsoring the Thursday night dinner. There's a couple of other tertiary sponsors, but they're the lion's share, and they've had a fairly significant reorganization or stand-up in Saudi, and Sultan couldn't be here, but he sent Haitham Al-Tawari. Is that close? Good, thank you. So he used to be the director of the Saudi Research Institute, and now he is working for the newly stood up Saudi Space Commission. And the head of that is our buddy Sultan, but Haitham is here to tell us all about that. So Haitham, the floor is yours.
Thank you, Steve. Good afternoon. So I'd like to talk a little about the future Saudi space activities, and I like to put the word future in there because many may not know that Saudi Arabia has participated in Saudi space activities for over 40 years. It started back in 1976 with the establishment of Arabsat and the utilization of Intelsat and Eutelsat. And in 1977, the King Abdulaziz City for Science and Technology was established with the role of furthering science within the kingdom. And we are very proud to have within the kingdom the first Arab Muslim astronaut, His Royal Highness Prince Sultan bin Salman bin Abdulaziz, and he was on board the STS mission 51G back in 1985, and he was the payload specialist responsible for the launch of Arabsat 1A. Fast forward a couple of years, space caught some traction within the kingdom, and the National Center for Remote Sensing Technology was established at CAXT. It was under a different name back then, but it's still the same center. It was mainly focused on remote sensing, and within it, a couple of years later, basically, the Space Research Institute was established as part of CAXT, and its main role was to further space research within the kingdom. Since 1990, Saudi Arabia embarked within SRI basically to work vigorously on human capital development and look at the engineers and the students and how to utilize and get the best minds working in this field. We were able to consolidate these efforts, and in 1999 we launched the first Saudi satellite developed in Saudi Arabia by Saudi engineers, and that was SaudiSat 1A. It was a an amateur communication satellite in LEO, but the main role of it was building human capacity within the kingdom to do such work. Fast forward about 15 years, and Saudi Arabia currently has 16 satellites that have been launched, the most recent being SGS-1, Saudi Geostationary Satellite 1, which is basically the first geostationary communication satellite done by Saudi Arabia. A couple of years later, it was recognized that there was a need to consolidate all of the work in the space field within the kingdom, and in December of 2018, we established the Space Commission. I'd like to talk about the mission. The mission is very dear to me personally. We all know the world had its Sputnik moment back in 1957. Saudi Arabia considers the launch of the STS-51G mission back in 1985. This is an old, this is not the right presentation because it should have the quote from His Highness. I'll basically say what it is. But coming back to where we were, the mission of His Royal Highness was essentially the Sputnik moment for the kingdom. If you look at the numbers and if you look at the data, there was a great increase in the science students and engineering students entering into that field upon that mission, and that drove STEM studies within the kingdom to new levels. So again, I like to use parallels. So 2018 would be our Apollo moment where we consolidate all our work, and we've achieved so much now that we have to do it better. So coming back to where we were, when the Saudi National Center for Remote Sensing was established, it was established in 1986. It was the premier receiving station within the region, and it covered a whole area of Middle East and North Africa. Since then, we've received satellites from data from a number of remote sensing satellites, all the way from Landsat, and this is not an exhaustive list. This is just some of the more recent ones. And we've covered a lot of area on Earth, and we've imaged a lot, and we can see the trend of the usage of data as it grows. In terms of research, CAXT and NASA have a history of collaborating together. Recent collaborations are the establishment of joint centers. For example, a joint center of excellence with Stanford University and NASA Ames, and another one with Caltech, where we are working on using technologies to solve problems on Earth, such as Earth surface change, looking for deep water aquifers, and developing technologies such as that. We've also participated with NASA Ames, and you guys may remember NLSI, the NASA Lunar Science Institute, which is now SURVEY. We are among the very first members to become partners with them and to work with them closely. We also worked with Stanford University in 2009 all the way up to 2012 on the Gravity Probe B analysis mission, and we're proud to say that a team participated and we were able to be part of that. Looking at the segments that our work was covering during that time, we were looking at satellite communications, Earth observation, satellite navigation, space security, space exploration. If we look at the activities I mentioned, we can see that a lot of the things that CAXT was doing falls within this. And also we had a number of notable projects that came out of this, that I mentioned some of them, but we were able to provide government entities with basically their requirements and needs of all remote sensing data within the region. We participated recently with the Chinese on their Chang'e 4 mission, lunar mission, where Saudi Arabia developed a camera payload for the satellite, and we were able to capture an image of Earth, and we also used that imager to help identify craters on the moon. We also done some research work with, as I mentioned, Gravity Probe B. We contributed in building the Saudi geostationary satellite 1 with Lockheed Martin and with Taqniya. Taqniya is a Saudi-owned company that works in space activities. Amongst the satellites that we developed, our biggest launch was in 2007, where we launched 7 satellites. Our first remote sensing satellite, SaudiSat-3, and also 5 LEO communication satellites, which were Saudi ComSat 2 to 7. The first 2 were launched earlier. We've worked with the universities. We've worked with the requirements and needs of the people, and seeing what we can do and how we can utilize space for that benefit. We also, oh, I'm going the wrong way, sorry. So this is just a simple graph that shows the satellites that we've launched. Some are still in operation, some obviously are no longer in operation, but we have populated LEO and we have now populated GEO, and hopefully we will be heading to higher Earth orbits in the future. Again, I said that the establishment of the Saudi Space Commission earlier was our Apollo moment, because it will consolidate all of the work that I just mentioned under one umbrella, and that is the umbrella of the Commission to better organize and better work with international agencies and universities, and basically unlock economic and social benefits and frontiers, both for the benefit of the kingdom and all of humankind. When we talk about our country's space program, we follow 6 key guidelines. Our space program has to be ambitious, overarching, aligned, peaceful, conforming, and engaging. And if I talk a little bit about each one of these, ambitious is we want to have an ambitious program that looks forward and fosters innovation. We are overarching because we want our activities to govern all activities within the space sector within the kingdom, and identify the applications and the value chains that benefit the kingdom. It's aligned so that it's conducive and enables KSA's vision 2030 and its direction as it's moving forward. Peaceful is very important. Our program is a peaceful program. Saudi Arabia is a member of the United Nations COPIUS, and our program looks at this as a peaceful program. Conforming as such that we adhere to all international laws, treaties recognized by the kingdom. And engaging is probably one that is very important and was pointed out by His Royal Highness. We have to have an engaging space program that will engage the public, the kids, the future generations, and help us move it forward. In terms of our policy objectives and at the Saudi Space Commission, we have identified 4 key elements or 4 key objectives. The first one is to stimulate economic development and innovation, and that is to propel the national space sector within the kingdom and use and foster technologies that will contribute to the sustainability of this sector within the kingdom. We are very keen on the human capital development. One key program that is very near and dear to His Royal Highness's heart is a program he calls Ajyal, Generations, which builds on students all the way from K1 to K12 and beyond that in the universities to develop and foster human capital development within the kingdom. We are very keen on fostering international cooperation. We understand space is something that needs to be done through international cooperation. I personally, for the past 10 years, have used this adage in which I like to say that we like to build bridges through science. And this is one very key element that we look forward to. And obviously to enhance national security. And this is through situational space awareness of possible threats such as asteroids and whatnot, and in addition to awareness in terms of the space environment itself. In total, from these 4 policies, we identified 18 programs with 3 main strategic themes that we are pursuing: an advancement theme, a new frontiers theme, and an enablement theme. The advancement basically is there to overcome the challenges currently available within the kingdom and to move our space sector forward. And such programs available in it, such as the satellite manufacturing, looking at developing a GNSS augmentation system for the Middle East that does not exist right now, something like that. In terms of new frontiers, we'd like to return to human spaceflight and foster the next generation of Saudi astronauts. We're looking at science missions. We're looking at possibly space mineral resources and possibly working with the US on the Artemis project and being part of Gateway. In terms of enablement, it is a key item since it is there to basically develop the means and methods of sustainability of this sector within the Kingdom of Saudi Arabia. And we do this by regulation, by building international partnerships, getting financial support, and essentially building our human capital. And with that, I would like to thank everybody, and if you have any questions, I'll be happy to take them.
Any questions?
One.
Oof.
What kind of launchers are you using? Do you have your own rockets, or do you go, I don't know, Ariane, or what kind of support do you have?
We've launched on Russian launch vehicles. We've launched XXXI on Ariane from French Guiana. So we currently don't have any launch capability, but it is one of the things that we will be looking at in the future.
Could you tell us about some of the missions that you are thinking about for the future?
That's a very good question, and it's a question that I asked all the stakeholders as we were meeting and developing our strategy. From my own personal point of view, we have to address the needs of the nation and see what needs are there and how we can resolve the things that they need, such as XXXI is one of the missions that came out of the discussions, but that was obviously many, many years before. But amongst the missions, there are remote sensing missions that we are looking at developing, the next generation of Saudi remote sensing satellites, also the next generation of communication satellites. In fact, XXXI is the first next generation next generation communication satellite in terms of the bandwidth it uses in transmission of data. Thank you.
Thank you, sir. So before I introduce the next speaker, I've got to fess up. I'm listed as the chair of this session, and I successfully offloaded all of the work onto Mike L.A. and J.D. Bartow. So they get all the credit or whatever. So our next speaker, Brad Bailey, is from NASA headquarters. He's the project scientist for the Lunar Discovery and Exploration Program. So, over to you, sir.
So I've been told I have 10 minutes to speak here, and considering the number of PhD researchers in this session, there's no way you're getting out of here before 6. So we'll see how it goes. And while we're waiting, Steve Clark is the Deputy AA for Exploration within the Science Mission Directorate at headquarters. His office is called LDEP, the Lunar Discovery and Exploration Program. And he's sorry he couldn't be here today, but since his, yes. Oh, I got it, thank you. And sends his regrets he couldn't be here, but says hello to everybody. So some background, I'm sure a lot of you are aware of some of this, so feel free to take a little nap for the next minute or two. But there was a Space Policy Directive 1 that was signed by President Trump a couple of years ago now. And in it, it talks about leading an innovative and sustainable program of exploration with commercial and international partners that will lead to the return of humans to the moon for long-term exploration and utilization, followed by human missions to Mars and other destinations. So that, in conjunction with Space Policy Directive 2, which talks about enhancing commercialization of the exploration of the moon, there have been a lot of new programs and efforts going on within NASA that take advantage of these space policy directives. Now, this is an image of paper by Shuai Li and Paul Lucy et al. From 2018 that showcases all of the different expressions of surface ice on the poles of the moon. And what you can see, let's see, is there a pointer? Maybe. very light pointer. What you can see is the light blue is all the ice deposits on the surface that you can see. And then the gray scale goes from warmer temperatures in the light gray to darker temperatures in the dark gray, and the blacks, it's really, really cold. So what you can see is most of that ice is all within these permanently shadowed regions on the surface of the moon. So with that ice comes a lot of exploration opportunities for sustained human presence on the poles of the moon. And so that is where we're ultimately trying to go by 2024 with humans. And I'll talk a little bit more about that shortly, I'm sure. This is a crater of Korolev from Mars. It's in the northern lowlands of Mars. And as you can see, there's also a lot of ice in this impact crater on Mars. And so when we think about exploration on the moon and then going on to Mars, really finding ice, finding resources that are available there, overall decrease the mass required for us to send humans beyond low Earth orbit. And so while we can look at the positive evidence that Mars has had a water cycle just like here on Earth, but ultimately climate change on Mars has changed it into the more dry, arid wasteland that we see here, there's a lot of things that we can still learn in operation on the surface of the moon that will inform us about how we can actually explore the surface of Mars as well. Now that said, I don't want this to be all about Mars because the moon is actually an incredibly valuable and interesting place to study from a science perspective. And so that is what our LDEP office is primarily dedicated towards, is the discovery of science, scientific discovery and overall exploration on the surface of the moon. What can studying the moon tell us about the inner solar system, the Earth-Moon impact history, overall planetary differentiation? We can also learn about radiation levels associated with planetary exploration by humans and robots, and then ultimately mitigation strategies on how to ensure the safety and effectiveness of our explorers moving forward. So this is our, what we call in NASA, the swoosh chart, and for obvious reasons, there's a big swoosh across the top. And you can see Artemis 1, starting there on the left in 2019, 2020, just keep pushing a little bit to the right, 2020-ish, you'll see Artemis 1, which is the first human spacecraft to the moon. So they're planning on sending Orion out and around the moon. Next is Artemis 2, the first humans, which will be in Orion going out and around the moon and back. And then we start building the gateway. And the first portion of the gateway that will go up there is the power and propulsion element, PPE, or the Solar Electric Propulsion System, SEP, depending on who you talk to. And that will also be able to provide communications relays back to the surface of the Earth. We also, from there, go on to a pressurized crew module that will be delivered to Gateway, and then finally, in 2024, we're expecting Artemis 3, and that's a crewed mission to Gateway and ultimately down to the lunar surface. Now, the Lunar Discovery and Exploration Program is largely a robotic precursor effort, and not only precursor, but it will continue on post Artemis 3. But for now, we are in the bottom left, you can see the commercial lunar payload services, where we actually go out and just like FedEx or UPS, we create an instrument package that we give to a commercial partner, and that commercial partner then takes it to the moon for us. And I'll talk more about that than you probably ever wanted to know here in a little bit. But we also are looking at the early South Pole Crater Rim missions so that we can go explore and figure out what are the volatile concentrations, what form are they in, what's their accessibility. And so we plan on sending a rover to the South Pole of the moon in late 2022 in order to start to answer some of these questions ahead of getting humans to the surface. So you'll notice across the very top it says Artemis Phase 1. there's a phase 2, and we saved money on graphics, so you have another swoosh here. And that's Artemis 4, 5, 6, 7. And there are a lot of other opportunities for these commercial landers to get down to the surface, where they can take new tools, they can take supplies, they can take scientific experiments and packages that can only be deployed by astronauts who can get down to the surface. Now that said, we're not only sending these CLIPS deliveries to the poles of the moon. There's a lot of really valuable non-polar research that can be done across the mid to low latitudes on the surface of the moon, such as looking at lunar swirls, these magnetic anomalies, looking at irregular mare patches, pyroclastic materials coming out of some recent in air quotes volcanic activity. And so there really is a wonderful opportunity for these commercial landers to provide significant input into the overall Artemis program, to where we have sustained human presence on the surface of the moon by 2028. Okay, so here it is, the Lunar Discovery and Exploration Program. I've already talked about CLIPS a little bit, but to be clear, we are planning on sending 2 commercial landers to the surface every year. The first 2 have been chosen, and I'll talk about them here in a little bit, but the ultimate drive is to enable community-driven science. We really want the lunar science community to be behind this effort and go and support us through solicitations and delivering their scientific packages to the surface of the moon. We also, I've already talked about instrument delivery and development. VIPER is the polar rover I talked about as well, and VIPER stands for Volatile Investigation Polar Exploration Rover. And ultimately, it's being built here at JSC with program management out at NASA Ames Research Center. We have plans for follow-on missions to that rover, where we're hoping to utilize different capabilities from the commercial sector to send new polar rovers, or new rovers to the surface, not just the poles again, but beyond. We're also looking at long-duration rovers. So, these first rovers are only going to be able to operate on the order of 3 to 4 Earth months or 3 to 4 lunar days. And so we really want to understand how to survive the lunar night. We want to understand how to do autonomous navigation and sampling, and so we're investing in that. The current Lunar Reconnaissance Orbiter is on orbit around Moon. It's been there for 10 years, and so we are currently operating that. There's also several lunar smallsats that we are looking at developing, and also the Apollo Next Gen Sample Analysis Program, which was we're currently uncorking, so to speak, some samples from Apollo that have been either kept under cryo storage or under noble gas storage. So they've been really reasonably unreactive since they were collected, and now we have new scientific analysis tools that can allow us to figure out exactly what those samples look like overall. A quick note about CLIPS. These are 10-year IDIQ, indefinite delivery, indefinite quantity contracts. I know that doesn't mean anything to anybody. I just started this job 6 weeks ago. It didn't mean anything to me then. It means very little to me now. But I am learning. And so ultimately, these 9 companies are part of a catalog that can bid on future opportunities to send missions to the surface of the moon. And so those services will be acquired through task orders that we issue. We say, hey, we would like to send these 6 instruments to this particular region on the surface of the moon. Tell us how much it's going to cost us to do that. And then these 9 companies can put together proposals and tell us how much they think it's going to cost us. Then we'll choose one based on price and past performance and overall capabilities of those companies. We've recently had an on-ramp for increasing those 9 companies because we ultimately need to land that bigger rover called VIPER on the surface of the moon. We plan on using a CLIPS provider to do that. Up till now, these 9, we had only planned on doing anywhere from 30 to 100 kilograms. The VIPER rover will be on the order of 3 to 350 kilograms. So we discovered that we need more capabilities from our commercial providers in order to do that. Let's see, we had task order selections already. I mentioned we had 2 Astrobotic and intuitive machines. You see on the board, there's 3, not 2. I promise I'm not that bad at math. Unfortunately, Orbit Beyond had some licensing issues and had to drop out. And so ultimately we're just left with Astrobotic going to Lacus Mortis, and Intuitive Machines actually is not going to Oceanus Procularum, it's actually going to the southwest corner of Serenity, Mare Serenitatis. And so, but those are expected to launch sometime in July, August timeframe of 2021. Again, we have several instruments that we're flying, and I don't need to go through each of these. You all have Google on your phones. You can look them up for yourselves. But the payloads are a mixture of scientific payloads, exploration types of payloads that can inform us about ISRU and the other types of research that are required to buy down risk associated with humans going to the surface, as well as technology demonstrations. And so the first one was internal NASA payloads. The second one's called LSIT-P. And I promise we're coming up with a new acronym for future payloads. But these, again, are a mixture of science, exploration, and technology demonstration. Okay, I've already talked a little bit about this, but we are ultimately wanting to make sure that we can rove around the surface of the moon and get at different samples. Landing in one place is great, but ultimately we want to get there and roll all over. If you saw the previous session, 10,000 kilometers, hopefully they're going to roll around. That would be awesome. But we are ultimately trying to figure out how to increase our overall mobility and access to different remote and these permanently shadowed regions on the surface of the moon. Simplex 2 is Lunar Trailblazer. That was just selected for a Phase A/B study, and hopefully if all that goes well, then we will select that for launch. This is something that's about the size of an average college dorm room refrigerator, and it has two primary mission instruments on there, the high-resolution volatiles and minerals moon mapper. If you're familiar with the moon mineralogy mapper from Chandrayaan-2, this is a follow-on mission to that. And then there's also the lunar thermal mapper that between the two, you can see between 0.6 and 100 microns studying the surface, looking at overall volatile content as well as the mineralogy of the rocks. And this is some of the science that we plan on getting done before 24 through the CLIPS program. And we plan on doing it through polar landers and rovers, looking at first direct measurements of the polar volatiles on the surface that will help ground truth some of this orbital data, this remote sensing that we've been doing from orbit for the last 45 years or so. So that's incredibly important. And then ultimately we're looking at the geology of the South Pole Lake Basin, which is the largest impact basin in the solar system, and then native mantle materials brought up through that impact that we're ultimately interested in learning about how the moon is differentiated. Non-polar landers and rovers, of course. We're also looking at doing orbital data, as I mentioned, from Trailblazer, and also getting started on in situ resource utilization. And leading to my last slide, 2 slides maybe, is that we are also producing an overall strategy for what types of science, what science needs to be done, what are the biggest scientific questions that could be answered from the surface of the moon, and then we're targeting all of our CLIPS instruments, deliveries, and ultimate participating scientist program packages towards achieving that strategy. And so we are looking at volatiles. We're making sure that mobility and sample return hopefully can make it into the mix in the long run. And Gateway will definitely be a part of this effort overall. We also have, as I mentioned, an implementation strategy with the crew, where only the crew and the science that's done from the surface can be done with humans and boots on the ground. So we are very keen in understanding how the moon is key for the next steps in human exploration of our solar system. And so with that, I think that's my last slide. Yes, thank you. Thank you.
Questions for Brad?
Yeah.
Thanks for a really good talk.
Thank you.
What about the science goal of visiting the South Pole Lake Basin, the
It is, and part of the problem, maybe not problem, well, one of the hurdles that needs to be overcome, of course, because the South Pole Basin is essentially on the far side of the moon, is establishing comms with the far side. And so you can conceivably do that with the Gateway once it's up on orbit, because it's in a near rectilinear halo orbit on the far side-ish. But there are other opportunities that we are looking into for establishing comms, and one of which is partnering with ESA, who is producing a lunar pathfinder comm relay satellite for the far side. There is also potential for using some of these commercial vendors to put a comm relay satellite in lunar orbit as well. So ultimately, it is one of the decadal goals. So the planetary decadal is a big document that the whole community comes together and says, this is what NASA should be doing. And the South Pole Basin is very high on the priority list for that decadal. And so we would love to get there, but we have to overcome the comm issue to start.
Once we start collecting the ice that's up there, do we have well-established techniques to convert it into fuel, to hydrogen and oxygen that we can use on the moon?
Absolutely not. That is a great question, and it's something that's definitely being worked into the phase 2 swoosh diagram that I was mentioning, and that's largely through the Human Exploration Operations Mission Directorate. But ISRU, in situ resource utilization, has been largely given over to this Space Technology Mission Directorate of NASA to head up as their mission. So through SMD, our goal is to characterize the ice and find out what its abundance and location and what form it's in, and then turn that data over to STMD and HEOMD to ultimately start to figure out how do we actually use it once we suck it out of the ground.
Brad, thank you very much.
Yeah, thank you.
So, I know you have more questions, but I promised Franklin an hour, so we need to hustle Brad off the stage. But thank you for coming from inside the Beltway to inform us. So, our next speaker or leader of speakers needs no introduction, but I'm going to waste 30 seconds here of your time. Franklin has flown 7 flights, tied with Jerry. That may be the most of anybody ever. I don't know. Certainly in the shuttle program. But that's not what I remember best about Franklin. Franklin and I had a conversation in late '85 or early '86 down at the crew quarters. I think it was a 2-beer conversation, maybe 3. And Franklin was telling me about how he got to MIT starting in Costa Rica. I'm not going to go through that whole thing. If you can ever get Franklin into a 2 or 3 beer conversation, it's a really inspiring story. So, without further ado, Dr. Franklin Chang Diaz and his panel. Come on up, guys.
Please sit down there. It's more like 4 beers, 5 beers.
We can spread out.
Okay, I'm going to do this quickly so that we don't waste too much time with niceties and stuff. But I'm going to go ahead and introduce you to this panel. This is the top-notch individuals in the field of nuclear power. And so starting from your left would be Dennis White. He is a professor of nuclear engineering at MIT, and he is the director of the MIT Plasma Fusion Center. So been working on superconducting magnets for fusion and some of the applications in fusion-fission systems, and he'll be talking about mainly that, superconducting magnets. David Poston is a chief designer at Los Alamos, nuclear reactor designer at Los Alamos National Laboratory. I've known him for, I don't know, maybe 30 years or more. And he's been working on all of the concepts that are being developed by NASA from very low power all the way to high power systems. Ron Litchford is a principal technologist at NASA headquarters, also nuclear engineer, and has been working on propulsion and nuclear power, nuclear electric propulsion, and nuclear thermal propulsion. So he'll give you a feel for both. And of course, you know Steve. Steve and I are going to try to sort of frame this whole story in a way that is important to crew members, so that we can talk about how we could get to Mars fast. So let me see if I can get the first slide. So this is just a notional concept of what a ship that would be powered by nuclear electric power would look like. And of course, this is a big ship. It would be something on the scale of the space station, maybe even a little bigger. It would have, you can see there in the back, 4 nuclear reactors. And these are nuclear electric reactors. In this particular case, they're about 10 megawatts each. So, and you can see those paddle-looking things. Those are radiators, because nuclear reactors require radiators to get rid of the excess heat. So these paddles are about the size of a little bigger than a basketball court, and they radiate on both sides, and they operate at very high temperature. Most of the cylindrical-looking tanks that you see are full of liquid hydrogen. So liquid hydrogen is the propellant. It's not a fuel. It is a propellant. So this is a material that then will be heated with electricity to produce a jet of plasma, and that's what will propel the rocket. In the back of the ship, there are 4 high-power electric rockets, such as the one that we're developing in our company, but there are many other potential entries on that. But the point is that these are high-power electric rockets. Now, the nuclear, the hydrogen that is the propellant is wrapped around, you can see the central core of this ship, and it serves as a shield against the radiation of space. So this is an important feature of these ships. They will provide shielding, and not just the hydrogen as a shield, but also internal to that. You can see there in the exploded view a set of superconducting, slinky-looking rings that wrap around in a toroidal fashion around the internal circular rays of the ship. This is a toroidal magnet, a superconducting magnet that will be operating at very high field, but the field inside the crew module is 0. So it's important that the shield is only existing in the toroidal band around the ship. So you have now a secondary shield. So you have a primary shield and a secondary shield. So this is the way you would protect astronauts against the radiation of space. So this is sort of the notional of what these things would look like. I give you a set of parameters, which might be important for crew members to see. These are all self-consistent. I'm not saying that these are the ones that we will use, but all of these parameters are self-consistent and give you enough material to actually develop a mission scenario. So you can see that we're talking about very high power, 40 megawatts, so 4 reactors, 10 megawatts each. We're talking about a ship that's on the order of 300 to 600 metric tons of mass. Obviously, this ship will not be assembled near the Earth. It will probably be assembled in the vicinity of the Moon, maybe near the gateway somewhere. And it will have a capability of delivering about 62 metric tons of payload to Mars in about a mission that would be fast. 95 days on this particular one. We could go faster if we were more ambitious and more, aggressive in the technology, but this is a sort of medium, still aggressive technology to be able to deliver humans fast. You can see there in the number trajectory there from 1 to 2 to 3 is the transition from the L1 to the Earth sphere of influence to the Mars sphere of influence, and then onto Mars is about 95 days. And later on you can read about all this. We'll make all this material available for you. But I wanted just to give you the frame, and then we can talk about the technology with the sort of the main course that will come with the rest of the folks. I wanted to leave a few minutes for Steve to say a few words about ops and about how life in a nuclear submarine, which is sort of the analog that we're trying to connect to, is. So maybe you can say a few words on that, Steve.
This working? Yeah, so you touched on a couple of things that are really important. Time, distance, and shielding. That's what protects us from radiation. Time, if you can make it shorter, that makes it better. Distance, not much we're going to do about that. You're going to be in the in the sphere where radiation exists. And then shielding. You've touched on shielding, but it all comes down to power. And power is sort of the key factor in this. I think the overarching title of this section is the Nautilus Paradigm. So looking back at the Nautilus, then you realize in 1954, when the Nautilus was commissioned, 55 when it first put to sea, and actually 60 years ago, next month, was commissioned the USS Triton. USS Triton was, I think, our 8th nuclear submarine, and it had 2 reactors. By the time we built the Triton, we had already built a pressurized water reactor on Nautilus, several of those. We'd already had a liquid metal reactor that we had sent to sea and operated. And Triton went to sea, and on its very first cruise, it did 60 days continuously submerged around the world. But it was a real piece of hardware. It really existed. And you have real hardware over at your lab that you're building. We have sort of been stagnated here with nuclear technology for a number of years. And so we kind of do need that step. Rickover was he built real stuff, and getting that stuff actually built and operating is really when you start to understand what you can do with it. There's no way we're going to be able to build at the same rate. But there actually has been development through the years, over the past 20 years, that the rest of the panel is going to let us know about that will get us that power. I remember talking when we were doing Prometheus many, many years ago, just the realization for science and exploration. We're not talking milliwatts, we're not talking watts, we were talking kilowatts of power for science and exploration on that mission. And it never came to fruition. But the excitement you could see talking to researchers and what communications and what research you could do with that much power was awesome. And now looking ahead from manned space flight to Mars with power, this is really exciting. So now I got to shut up and turn it over to people that can actually talk about this stuff.
Okay. All right. Thank you, Steve. So Ron, you're next. Would you like to come and do the slides from here? So Ron Litchford will give us a NASA perspective. So here you go.
To the next one. Okay, thank you, Franklin. I do work in the Space Tech Mission Directorate at NASA, and I spend a lot of my time thinking about technology, what the future holds, what we'll need, and trying to develop strategic plans for producing the technology that we could infuse into those missions. And so what I'm giving you today here is really just my perspective on that, based on all the thinking I've done over the years about it, where I think we may be headed, and what I think we maybe need, and what that implies for technology development. So this is just a big, a graphic to kind of share with you my high-level thought about the future. It encompasses science, exploration, commerce, and security. I believe all of those 4 will be in the mix. That's my impression at this time. And I've kind of broken it into 3 spheres is how I see it. We're currently in the midst of Sphere 1 activity. That's really cislunar development as we, as a prelude to moving out to Mars. And the previous presentation on lunar development, I think you saw the Artemis program and CLIPS program and what we intend to do there. There's a lot of science payloads that are going to be sent there, and I'm not going to go into that in detail, but beyond that, there's a lot of, I think, commercial opportunity that people are looking at, and I won't list all of those, but you can read through that list and think about whether you agree or not, but those are things that people are discussing, making plans for. I have no idea whether they'll really make a business case that closes on any of those. I don't know. I'm a cautious optimist, though, and I know there are people with either deep pockets or access to deep pockets and a deep commitment to trying to do it. So I think we'll find out over the next decade or two whether some of those play out. And on the bottom, there's a few things that I added on the bottom of that sphere that I think are emerging of importance, and it's related to security. And there's a lot of discussion now about the Space Force, you know, and what's going to happen with security in space and how we may need to expand and what we're doing beyond today. And so I think, you know, there's certainly going to be if the commercial part works out, there's going to be a need for somehow projecting rule of law compliance. And certainly planetary defense is always a subject, and I think we'll have to build assets there at some point in the future to help us with that. And certainly space national security assets will most likely expand beyond surveillance that we have today. That's my guess. And so the implications for that, for technology, when you think about the cislunar environment, the delta V requirements for most of that, it's not that bad. It's like 5 kilometers per second delta V. So you can do a lot of that with chemical or solar electric propulsion. But really, as we start expanding out to Mars and we think about kind of having mobility, the kind of mobility we really want, and I'm going to make an analog connection here to the paradigm now. Nautilus paradigm Steve mentioned, that really we need to be thinking about littoral and blue water mobility capability. That means, you know, being able to move assets rapidly and efficiently and not just have one single mission use. They may have to have multiple uses. So that's going to require, I think, advanced technology beyond chemical and electric propulsion. And so I think that will drive a lot of what we do. And over the years to come, I'm certainly, if we can get the advanced propulsion, you know, there's a lot of deep space destinations we'd love to explore beyond Mars. Mars for sure, we'd love to get humans on it. But there's a lot of deep space, you know, destinations. If we could get there quicker and more efficiently, we could do a lot more missions and learn a lot more about our solar system. And I think the last sphere I have there is interstellar, and there's been a lot of talk about can we send an interstellar medium probe? Can we actually break free of can we penetrate the heliosphere and actually break free of the solar system gravity well? I think that is a mission that's attracting a lot of discussion now. And so maybe sometime in the future decades that we will actually mount a flagship mission that will actually do that. Let me move on. I'm going too slow here. So when you think about, we need advanced propulsion, right? The first thing I do is like, okay, what's my options? And then what can they do and will they work? And this graphic tries to capture that. So what I'm showing here is the different, you know, propulsion technologies, basically the technology landscape we have to choose from that we know of or have access to. And they're showing you the specific impulse of those technologies versus the type of vehicle acceleration they can produce. And the key point I want you to bring away from this is if you look and you think, okay, I want rapid transit, and I'm going to define that as being at least 10 to the minus 3 Gs. We've sort of a lot of mission studies say that will get us the kind of capability we want. And we need it to be efficient, at least 1,000 seconds ISP, right? So then you can block out everything I've got in red there. Okay, that blocks out everything else. It's shaded in red, and then that leaves what's left over is what can actually work. And what's really interesting here is everything that's shaded red is what we know how to do today. Everything that's in white, we really don't know how, we haven't done it. Other than nuclear thermal propulsion, which we have at least developed the technology back in the Minerva rover days to do that, it doesn't exist. So this just shows you the technology challenge, the real technology challenge that we're facing. And so it really comes down to either NTP or NEP. They both can do a good job. NTP can do really high rapid transit, but it has an efficiency problem. Even at 1,000 seconds, it's not truly what you want. NEP has much more promise, but it's a much more lower maturity state. So let me go on. And so these are some of the options that we've been looking at for deep space transport to Mars. You probably recognize some of these. The only thing I would want to bring out probably just a few points to bring out here is the things on the left. You have chemical at the top and then a hybrid electrochemical at the bottom on the left. Those are things we know how to build, but I just showed you they don't do the rapid transit that we want. So we can do missions with those, but they're going to limit you to what we call long-stay Mars missions. So you're going to be gone a long time, and you can really only do what we call opposition class missions, and they're just long missions. If you move to the right, now you move to the nuclear side. You have nuclear thermal or nuclear electric. Both of those have the potential of doing what we call conjunction class missions, which means you have short stay, much shorter missions. You don't have to spend so much time in space. You go there, you do your mission, maybe it's a month, whatever, and then you come home. And so these have a lot of promise for that, but they're also immature. And I'll speak a little bit of what we're doing to try to address that. First, I want to show you, okay, I said NTP and NEP both work, right? How do you choose which one, right? So this is just a baseline calculation to kind of tell you when would you choose NEP, when would you choose NTP. So this is the results of an analysis that was done to look at, let's assume you had 100 metric tons in Earth orbit, you wanted to take it to Mars. Okay, how much using different propulsion technologies, how much could you get there in terms of the payload out of that 100 metric tons, and how long would it take you to do it? And so you can see on there at the very bottom is chemical. So you're not going to get much of your payload at all, and it's going to take you a long time to get that there. It's not an attractive option, right? So you step up to NTP, the next step up, for different ISP levels assumed, and you can see, oh, now I'm getting much more significant fractions of my payload there. And I can even increase the trip, to reduce the trip time to something that's really interesting if I'm willing to give up some of that payload, trade payload for trip time. But it gets you in a much better position, right? Much better position. And then the blue curves that's in a 60% NEP calculation, assuming, I think this was a 5 or 10 megawatt reactor. And you can see what you get with NEP is it better or worse? And it really depends. And it depends primarily on one parameter. It's called alpha. It's a specific mass. It's how much this thing weighs or how much mass it is divided by what kind of propulsive power it produces. And what you find is when you get down to 10, it's competitive, right? So you can see 10, yeah, I'm sort of trading well with NTP, but okay, it's about the same as NT. Maybe I just do NTP, maybe I forgo NEP. But where NEP really shines is when you get that down to, say, I think 5. When you get down 5 or below, then you really get into a position where, kind of the situation where you can go fast and you can you get a large payload mass fraction. So that's why we really think NEP has a lot of huge promise, but it also has the most technical challenge too. And this is an interesting chart. This just shows you what space nuclear power systems and what have we flown, what have we studied, what's really just notional. And the main thing to look at here is the bottom is the total power of the system, and then you look at the alpha is what I just discussed on the right side, right? We'd like to get up to 1, right? Or not 1, but we'd like to get below 5, really. And you can see low alpha NEP up there. But you look at where we are now, and we've really only flown a few reactors at very low power and very not really great alpha. And we've studied a lot of things in between. So it just means there's a lot of technical challenge between here and there, what we want to be. So I want to follow on the Nautilus paradigm. I want to say, okay, what do we, if we wanted to build a reactor for space, for propulsion and power, what is the challenge and what is the potential? And this is just a look at that. And what you have to look at here, I think, is you look at the alpha of the whole system, is it really breaks into 2 pieces, your power part and your thruster part. And the thruster part is something that I think we've done a lot of research on. I think there's a good solid pathway to achieving the type of alpha we need for the thruster. What's really been the key challenge we haven't really addressed well is the power plant specific mass. And so this is just an example of a type of system that's been proposed that could address that need. This is basically a gas-cooled reactor concept, and that reactor there in this system operates at 1800 Kelvin. So it's really, really hot, and there's a reason for that to get the alpha down. But it's sort of, you're getting up there toward NTP temperatures, but not quite so hot that it's something that you could have hope that you could build and still have a long life in it. But that's a system that we've looked at in the past. One of my Japanese colleagues came over some years ago, and he spent a year with me. And one of the things we did was look at that system in detail. we try to develop a model for all the different components, and then, well, we're going to calculate alpha, and what is the alpha of that system? And this just summarizes the results that we found. I would be the first to admit that it's not a high-fidelity study. It's not a point design. There's a lot of technology assumptions that were made in producing that chart, and that would require technology advancement, but it was things that we felt were realistic advancements and could be done. And what you find is that, yeah, we can, this system, based on that analysis, could get down to alphas that are really attractive and in the range that Franklin was mentioning in the concept he proposed at the beginning of his talk. And so one thing to take away from that is that alpha gets better when you go up in power, of course, and it also requires you not only to have a hot reactor, but a hot radiator, and that's to keep the radiator mass. You need to be hot so your radiator doesn't just become enormous and kill your whole, kill your whole system design. So this is almost my last chart. This is just a very high-level chart of what we're doing in Space Tech Mission Directorate in terms of, I call them development vectors. It's very high level. And we're doing quite a bit of work in the chemical side. We're doing work to support, hopefully support the Artemis program down the road. We're doing some storable work that's right now supporting some of the CLIPS providers. And when there's a lot of cross-cutting technology work, and you can see how it links into all of these different development vectors. But what I really want you to do is look down to the nuclear and see there's a couple of paths going on there. The thing that we're investing the most in today is for rapid transit, is NTP, and we're trying to get to, I have BFR, that stands for, we're trying to get to a big fission reactor, right? That's something, when I say big fission reactor, that's like 500 megawatts, something on that order. So it's really big. And that's where our primary investment has been and probably will continue into the future, although we continually look at how can we help NEP in the process. And you can see NEP is underneath that. On the SEP side, we're doing I think it was mentioned, we're doing the high power solar electric propulsion for efficient transit, and we're working, that's going very well, and we're going to fly some things soon on that for the Artemis program. And so I think, and there's a lot of high-power thruster work. So there's high-power thruster work being developed under that could be, I think, infused into the nuclear electric as well. So the strategy we're pursuing here is develop NTP, develop SEP. But when you do so, try to do it in such a way that the fuel you develop for NTP can be leveraged and brought into the NEP, a multi-megawatt NEP system down the road. And the thrusters that you're developing for SEP can be basically SEP-derived thrusters that go into an NEP system as well. That's really the strategy we're trying to pursue. And underneath all of that is really we're always continually do some small research efforts that advance concepts that may become real in the future. So this is my last chart. I hope I didn't go too long. This is just when we did the Nautilus program, Admiral Rickover was the driving force. And it's not just technology challenges. I think it's leadership as well. And I think, Admiral Rickover was a man of his time. And a lot of the things, and these are just some words that I brought quotes that he has said in the past that I think are pertinent. They were pertinent in his time and for his challenge. I think a lot of what he says is pertinent for our time and our challenges as well. So I will walk off the stage and leave those for you to read yourself. Thank you.
Thanks, Ron. Dave, you're next. Give us the nuts and bolts, I guess. Right there.
All right, hi. I'll wait for my slides to get up there, or do I do it right here? Forward?
Just go forward. There should be one more.
Okay.
Yeah.
Cool. All right, I work at Los Alamos. I work on reactors for special purpose applications, and space reactors are my passion and what I've been working on for a while. We finally have something cool to show you. I probably won't spend too much time on what reactors can be used for, because everyone's heard that, today and ad nauseum for decades, right? We know all the cool stuff we need reactors for. And everything on that list can be done. I've got asteroid comet defense on there for Ed Liu, who's here, that I know we could use. Really, when we're talking mostly about transportation today, and it's true that we need rapid transit times, I think, just for less time in zero-G and less risk away from home. I mean, one of your biggest risks is just not having a hospital nearby. I do take exception to people using radiation as a reason why we need to travel fast, and I really think it's important. I like talking to astronauts because they generally understand risk and can put risk into perspective. And when you're talking about a mission to Mars, you're going through launch, trans-injection burns, captures, landing launches. I mean, all sorts of acute risks, besides the risk of just, again, being home and away. But we're generating our policy based on a 3% chance increase in cancer, based on a model that's been proven bogus by most recent science. And so everything right now NASA's doing, they're worried about the astronauts getting the 3% risk of increase of cancer. And if any astronaut that's on the launch pad, that's their biggest concern, I don't think understands the risk. So I want you guys just to always push back a little bit on the radiation thing, because it's not that big of a risk. It really isn't. But what we do need is the fission power to do everything we want to do, burst for surface power. The other thing astronauts understand, you want to have a reliable power source, right, on the surface. And that's what these early generation reactors can do. So that's what we're focused on right now. And as we heard, reactors technology has been stagnant for over 40 years. Not just space reactors. We launched a reactor in 1965. The SNAP-10A, and there hasn't been a space reactor built or tested until recently, so over 50 years, with billions of dollars spent. Even worse is just terrestrial nuclear reactors. The Department of Energy has spent billions and billions of dollars on advanced reactors with no results. And a lot of that is it's become really hard to test. I mean, we put in ourselves fear of radiation. It comes in all forms, and it really has stifled humanity in a lot of ways. And one of it is it's so hard to test a reactor that we haven't been successful in developing a new reactor in all that time. And so we wanted to come up with a path to start developing, building, testing reactors. We started off with a Duff reactor test in 2012, and then last year we just completed a Krusty test, and I am a Simpsons fan, if those names sound familiar. So that's I'm just going to talk quickly about those and then talk more how we get to the good stuff. But the cool thing here is we designed, built, and tested a reactor. The first truly new reactor concept in the United States in 40 years. It used highly enriched uranium, which is another thing, if we're serious about exploration and expansion into space, highly enriched uranium will help you a lot over low enriched uranium. And that's another political battle that could use support because there's safeguards concerns with HEU, but we can protect it and use it. In fact, Krusty used highly enriched uranium. We shipped it across the country, and it worked great. So we have Stirling engines, if you're familiar with power conversion technology, hooked up to a reactor with heat pipes. Liquid metal heat pipes are unbelievably good heat transport mechanism. They're simple, solid state, except for the sodium that boils inside the heat pipe. Vapor flows down to the end of the heat pipe and condenses and transfer heat. And they work fantastically. No one had ever operated a heat pipe reactor until this, and it worked beautifully. So I'm not going to go through these charts. It's just the reason I put it up is to show this is the first time there's been new data from a new type of reactor, again, in 40 years. So the cores on the right, it's highly enriched uranium is the rusty colored, gold color stuff, and then there's heat pipes, which have sodium inside them, that transported the heat out to our Stirling engines. The reactor here proved that how simple it is, the physics, really keeping the physics simple, the reactor is the most important thing because of our inability to test. It's because if you keep the physics really simple, then your engineering can be real in terms of impurities or tolerances or technologies we can use. And so all of our concepts try to keep the physics as simple as possible so that we can actually engineer the system. But we did demonstrate that on the picture on the right shows, in the back you can see the Stirling engines. Those are all the thermocouple wires coming out so we could get a lot of data. And this is the coolest experiment we did, where we showed that the reactor load follows the power conversion. So if you want to produce more electricity, You turn up the stroke on the Stirling engines, which just causes more gas to move back and forth, heat transfer power, move your alternator more to get more power. And so during this test, we didn't control the reactor. In fact, we never need to control the reactor in this kind of reactor. And so the core is at 800 C, pretty hot. And see, it stays relatively constant throughout that whole transient. And what we're doing is changing the power draw. And see, the power goes down to 2 kilowatts and up to 4 kilowatts, with the power staying essentially the same just by us drawing more power or drawing less power from the system. And we also showed that we can handle failures, failure of Stirling engines, failure of heat pipes. This test, we looked at what happens if we do fail a heat pipe, show we can still produce full power. And so it's one of the really nice features of the heat pipe reactor. And right now, out of Ron's office, STMD at NASA, there's a kilopower project, and we have a bunch of designs for these reactors. There's 1 kilowatt designs for space science. We do have a short supply of plutonium-238, which is what we use for our really ambitious space missions like Cassini and Galileo. These reactors could provide even more power for those kind of missions. One that I'm pretty excited about is a 10 kilowatt NEP mission. It's lower tech than GMO. GMO was ambitious and a little too ambitious. This is a 10 kilowatt system, but it's still useful. It enables orbiter missions to planets, outer planets, and moons. But then right now, what we're really looking at is the 10 kilowatt demo on Mars or Moon for ISRU demo. Because the biggest thing ISRU needs is power. Well, I think we understand the technology pretty well. It's really just how we're going to power the thing. And so we're looking at taking a 10 kilowatt reactor, putting it on a lander, working on a project right now for that to provide power. You can take about 4 of those or 5 of those. You've got enough for a bare bones human outpost. I mean, just a mission. You'd like to have more, and you probably would. Most people would feel much more comfortable with 100 kilowatts, and we can go to a 100 kilowatt reactor if we need to. But this whole design approach goes to about 1 megawatt, 2 megawatts of power. And they're all rooted in the test we already did, and the physics are exactly the same. This is the kind of chart that kind of puts things in perspective from what's been done and can be done for reactors. The biggest risk for reactors, the biggest one in my belief, is keeping the physics simple because of our lack of ability to test. We would need tens of billions of dollars probably to create a test facility and actually test these rockets or reactors on Earth. So we're looking at space testing, right? Testing, but if it doesn't work in space, you don't have the diagnostics really to know. Diagnostics is a huge issue because it's really hard to know what temperature you're at, even on the Earth when you're up at 2,000, 3,000 degrees, let alone trying to get the data in space. So the greener reactors we built, the yellow, the crusty, and the NTR XE prime were prototypes. And then we look at the GMOs on there, SP100. The one thing I like to show is that so for NEP systems that are practical, not game-changing, I would say they're still game-changing. Alphas at 10s, alphas at 7s. Those reactors are very simple. The power conversion gets tougher as you go. At 10, we can use state-of-the-art stuff. Then you're just getting into the really hard technology development programs to get to the lower mass. But the reactor physics, and we can keep the reactor simple so we can do it. And really, NTP is incredibly hard. And they showed that in the Rover Nerva program where they did a dozen real nuclear tests, and we're still a long way from flight. But those were systems we can do, and they're actually very simple. Those were actually simple neutronic systems. They use those. So I'm trying to help convince NASA to go back to a simpler NTP design than what they're looking at right now. But you can see, especially when it's replotted on a linear scale, how much higher power density an NTP system than would be an NEP system or other system. I only made this for the IMAX audience, so but it's what I want to do is get something done, like everybody here, right? Start exploring space. And so I think we have a good development path with the kilopower program. We also have a project right now called FD1 and NTP that would actually take the first step both for higher power, surface power, and to show we could do NTP, do all the control diagnostics and everything. So, you know, all the numbers are fiction anyway, but they're my version of fiction for what the odds of success are. But I think, again, due to the difficulty of testing, you know, we got to start out simple and build from there. So this is really just, I think we have a path. The big problem is people don't want to fund something. It's called mission pull, right? It's hard to get Congress to fund something unless that thing you're doing right then is going to give you some great benefit. And we never get to the point where we take a step to get to what we really want. That's why we came up with the Kilopower Krusty program, because along the way we're getting useful reactors. If we get 100 kilowatts or 2 megawatts of reactor, we can use that on the moon or Mars. And then, oh, by the way, that evolves to a nice NEP system. So that's really what my bottom line message is. It's, you know, we did develop a reactor for $18 million, 3 years to design, build, and test a fission power system. We were told we were crazy. And in general, you know, NASA and DOE, in a lot of ways, want things to be expensive. You know, it's what we might call white-collar welfare, you know, to get money to centers. And I don't have many friends, as you can tell, but because I say politically incorrect things. This was the first nuclear test of a space system in over 50 years. I mean, that's pretty cool. We need to keep taking small steps, and you know, for $80 million, we priced out the reactor that could do the first NTP mission in the 100 kilowatt electric surface system. And it's very reasonable to get to megawatt. The hard part's getting to power. And human propulsion is going to require several development steps. I mean, we're no closer than we were 40 years ago. The things we got going for us is advances in manufacturing. That's going to help a lot on the technology side. The thing working against us is it just gets harder and harder to do real nuclear things, which is the reason to make systems that we know are going to work without requiring a lot of full power tests. You know, and a lot of the rover and Irby experience is awesome, but it doesn't really apply to what NASA is looking at right now at all. And it'd actually be a good thing if they went back to that. But you know, and that NEP, I actually think NEP is ultimately what we'll end up with, because it's an easier, more straightforward stepping approach to that. And it, by the way, it's much more capable. I mean, you can keep going to higher and higher ISP, more capable systems. All right.
Thank you, Dave. Thank you.
Pardon me to everybody, man.
No problem. Dennis, you're next and last to give us a flavor on the emerging technologies.
Well, thanks, and thanks for the invitation to come here. So this is a close-up of what Franklin was showing before. So the idea of using magnetic fields is not a new one, and it's really quite simple, actually. Magnetic fields deflect charged particles, particularly energetic charged particles, and if you want to deflect more energetic charged particles, which are the most problematic ones with respect to radiation dose, then you need stronger magnetic fields, or you need to build the magnetic field really big. We have one around us right now called the magnetosphere, and to put this in context, it's actually really simple math. It's actually the product of the field, basically, and the size of it. So for the Earth, a Gauss basically works, because it's the size of the Earth. If you want it the size of a spaceship, it has to be these kinds of numbers, 70,000 Gauss. So I'm going to switch to Tesla because I can't work in that unit system. That's 7 Tesla. So what's the idea in this? Namely, you build a superconducting magnet. It's superconducting so that the electromagnet does not consume electricity, because in the superconducting state, produce a continuous magnetic field and basically produces a deflection mechanism that saves the inhabitants from the inside from being irradiated strongly by that. So this was something that was done several years ago and led out of MIT. And there was something in this called high-temperature superconductors, which at the time were extremely speculative. In fact, were basically pieces of crystal in a petri dish in a laboratory. What's exciting about this is that this is really around what you call disruptive technology. That's maybe sometimes an overused word. And this is what you wait around for in a career like mine. This is the most exciting thing in my career by far. I've worked in magnetic fusion for 30 years, and now I've basically dedicated my career and the rest of my career to developing this new technology. Why is it such a disruptive technology? Won the Nobel Prize in 1988. These are famous because they were superconducting materials at liquid nitrogen temperature, which is incredibly easy technology. But if you look at the plot that's up on the top left, this is the volume in which superconducting materials exist. And it also turns out that they will cease to be a superconductor, not if they just get too hot, but also if you make the magnetic field too strong. And remember I said, we want strong magnetic field. So basically, if you look at the old technology of superconducting materials, this new technology in this volume of what the superconductor will work is an improvement of a factor of 1,000. And when you're an engineer and you're designing something, that is an amazing space. I explore a different kind of space than you guys, sorry. It's this space. So what does this mean? What does this mean in practice is that all of a sudden, instead of a few Tesla magnetic fields in superconducting magnets, we can go now to 20 Tesla at the coil. And this is not science fiction. This is happening in the laboratory right now, and the leading laboratory to do this is my lab at MIT, where we actually attracted private sector funding from the likes of Bill Gates and Jeff Bezos to develop these magnets for fusion energy, because this new technology is basically a factor 50 improvement in the economic viability of fusion. And our plan is to actually have a working prototype in 5 years, because we're shrinking the size of the devices by a factor of 50. But I want to get to what this means for this, is that we actually, and I love teaching engineering design classes, by the way, of which at the beginning of every one, Rickover's rules of engineering are cited, and we go over this. And sometimes we break it because we start making complicated things, and then we try to simplify it. So what does it mean, this new technology for space propulsion? So we took a look at a few different things, which I'm actually not going to go through in detail, but it's actually linked, in fact, to Franklin's company, and I'd like to link it back to that, to magnetic plasma propulsion. Is that it turns out you have to have magnetic fields which are inside of that. That's how Franklin and I got to know each other a few years ago on a fusion panel from the National Academies. So this new technology will affect that thruster, but it actually had effects throughout this entire system, including a new kind of, actually an old but reinvigorated idea of a fusion mirror to basically drive a subcritical fission blanket that produces around 30 million watts, 30 megawatts of fusion power and fission power. MHD generators, which are essentially motion-free, no moving parts generators to convert thermal power to electrical energy. So these are, we looked at all these in a class I taught last year, but I really want to get to this one, was that I got very excited about the use of, in fact, the HTS for a slight reinterpretation, in fact, of what Franklin had shown, which was the idea of the astronauts living inside of a magnet. And the magnet itself is a donut or toroidal shape, which itself is spinning. So of course you get the centrifugal force for the artificial gravity in this. But there's superconducting magnets embedded in the outside part of this. So what happens is you get a cartoon that looks on the right of the strength of the magnetic field. You get an extremely strong magnetic field close up to the coil, and it's actually, what is essentially making is, it's mimicking the Earth's magnetic field, because it's produced by a dipole, by conducting currents which are in the center of the Earth. This is producing a large magnetic field which is going out and around like this. The new thing in this is that the ability to make this deflecting magnetic field is improved by at least a factor of 5 compared to previous superconducting technologies. So as an example, what does this mean if you put this habitat? So remember, on the right, the astronauts are living inside, and you can see the size of it. It's actually quite large. It's about 12, 15 meters in radius. That this is for 100 MeV solar protons. This is the top end of what you get, for instance, in a large coronal mass ejection, which those ones, by the way, if you get caught in a big one of those, the intense, that actually will be in acute doses of radiation, so you do have to worry about it then. So you can see so what you're seeing is that the blue part of this is basically the absence of charged particles in that area. So this just is working just like the Earth's magnetosphere, that it's basically deflecting away the plasma wind, but in this case it's a hollow sphere, so basically there are no poles, and the charged particles just go through the center of the magnet and basically miss all the habitats. So in this one, it's fantastic because it's basically 100% shielding, because the protons never hit any material, they just get deflected around in the magnetosphere. And by the way, it'll light up literally like the Northern Lights. And this was very interesting to me because I'm a nuclear physicist and a plasma physicist, is that the idea that you could build a habitat that actually protects against the background cosmic radiation, which has these very high energy particles, and sort of the peak of this, the most problematic are giga-electron volt protons, which are extremely high, is that the magnetic fields that are now accessible with this new technology, in fact, deflect GeV protons. And this means that you're now, if you take into this and a combination of the self-shielding that Franklin was showing before, you really now have within your grasp the ability with this new technology to build really self-shielding habitats based on this new magnet technology. So we're doing this. By the way, this is exactly to what, in the same vein, I got tired of paper study after paper study. No more paper studies. Right now at their lab, we're building basically a version of this magnet technology, which will surpass these magnetic fields. It's going to weigh about 10 tons. It's about 3 meters high, and it will reach the conditions actually necessary for that. And that's going to be built in the next year and a half, because I've had it with paper studies. We're going to build a real thing, and if we fail, we're going to fail spectacularly. But if we succeed, we think it's going to change the world actually because of access to fusion energy. But I want this to change science and lots of other things as too, because it's an extremely exciting new technology. So thank you for your attention.
Thank you, Dennis. Any questions so far? Yes. Thank you.
For space travel, it'll take just a second for them to get it. Okay. Hello? Here. Okay. Hello?
Whoa.
For space travel, I think we have 2 problems. One is radiation, and the other one is gravity. Gravity is because in the body, the skeletal and muscular system is affected, the immune system is affected, and also your ability to grow plants for food is affected. If you have gravity, you have solved all that. So, the 2 combined would be very nice.
Yeah. Yeah. Did you want somebody to make a comment on this?
And of course, I'm a big fan of 2001, so that's...
Yeah.
No, but you're right, it is true. This is why circular geometries are intrinsically good to these things, because you can basically use them to your advantage in this. One of the health effects that we don't know about, which would be interesting, is what happens if you're inside, because it turns out you have about half a Tesla background magnetic field. So we haven't held people, it's very common, much lower magnetic fields in MRI machines, but for long periods of time, we're not sure what that will do.
I've got
but it's probably not as bad as the lack of gravity.
Yeah, we've got some mice we could give you, and you can, but the question is, if you're going to Mars in 95 days, are you also creating a gravity field from the propulsion?
Very little. Yes, the answer is yes. Very small. Probably micro Gs. But it's all related to power. The higher the power, the more gravity you get. And that's the best kind, the one that you get when you step on the gas, you know. Yeah, so. Any other comments?
Yes, I have one
Yes,
here, up
Vance.
here.
Yeah, a question about demonstration of either a nuclear electric or nuclear thermal engine. We'll only have the space station around for, what, maybe another 5 or 10 or so years. It seems to me that an engine like that, one of those concepts needs to be tested in space. Would it be safe and would it be practical to put a demonstration engine of either type on the space station?
Anybody like to take that on?
It would be, well, I would say it would be safe, but policy-wise, I'm not sure if it would pass the safety test. So, go ahead.
Yeah, there's a UN treaty on that about putting reactors in low Earth orbit that was, I think, signed in the late 60s. It's been updated a few times. And I think that would be a major hurdle to overcome just to do testing. Yeah, safety, I don't think, in reality, it probably would be very safe, but
Yeah.
there are hurdles to climb.
And that's the same for nuclear electric.
Yeah.
Well, the only difference is that the electric engine doesn't care where the electricity comes from. If it comes from a nuclear reactor, wonderful. But if it comes from some other source, then you can still test the engine itself. That's exactly what we're trying to do. In our world, I mean, electricity is wherever you can get it. And one of our biggest problems on testing high power electric engines is the vacuum chamber. I mean, we are having really serious difficulty with the very large vacuum chamber we have here on Earth. And if we're talking about testing multi-megawatt, electric engines, plasma engines, there's no vacuum chamber on planet Earth that you can use to test these engines, especially if you're going to turn them on for 2 months or 3 months, which is what you need to make sure that they run for. So we'll be testing them on the moon. So the moon, to me, that is the real value of the moon. It is a testing ground for the high-power engines that we will need to go to Mars.
Okay.
And the electricity on the moon may come from solar. We have plenty of room to have lots of solar farm, a big solar farm on the moon. There's plenty of sun. So we could do that. And we could also put a nuclear reactor. But that is something above my pay grade. That would be somebody.
Okay.
Somebody needs to decide that.
Let me add something to this, Franklin. Ideally, in either case, we would ground test the system thoroughly on the ground before we ever flew it. And that's not trivial, especially for NTP, because we can't test like we did in the old days. But we are looking at methods for overcoming that. And there are solutions, but they're hard and they're expensive. The other alternative, we are currently looking at a flight demonstration of an NTP bypassing ground development. But it would not be on the space station. This would be a free flyer. And it's seriously being looked at and studied. It's a future option. It's on the table.
Okay. And
I have a question up in the balcony.
just one other question. We're starting to have a few electrical cars around. If the world turns from cars that we have now to nuclear, I mean not nuclear, electric cars, we're going to need a lot of electrical power plants. And won't we have to get over this terrible fear we have of nuclear to get the power plants to support those cars?
Yeah, I like to say there's no such thing as clean energy. The only clean energy is the energy you don't mess with, because entropy always increases. So whether it be nuclear, whether it be wind, whether it be solar, I don't know if Don's here, because we had a long discussion one day about the fact if you took solar panels and you paved the state of Pennsylvania with our current efficiency rate, that would about replace our electrical generating capacity, but who's going to pave the state of Pennsylvania, and what effects would that have? Or, you see a few dead birds around a windmill, you say, it's just a few dead birds, and you think back, and the guy with the first internal combustion engine said, what's a little smoke? So there's consequences to every decision we make. So ultimately, it's going to be efficiency. There's a balanced solution out there. Nuclear power has to be a part of it. The only way to get to fusion, which is, it's sort of everybody's, what's the good word for it? Pipe, no, don't say pipe dream. You're going to get there. It's the Holy Grail, right? If we ever get to fusion, we're not going to get there by not doing stuff in between.
It's actually physics. You have to get there.
Yeah, physics gets it.
Physics has to get you there. Physics has to get you there. It's because you need energy density in the end. There's two things on Earth that is not using fossil fuels that will get you that. It's fission and it's fusion. It's physics. And public opinion can be what it is, but that's just the reality of physics.
I have a question.
Somebody
up in the balcony.
I cannot.
Here?
Okay, go ahead. Yeah.
This panel is looking in 50 years into the future.
Yeah.
And I don't know if any of y'all have read Robert Zubrin's latest book, The Case for Space, in which he deals with the thought of fusion power with helium-3. So do any of y'all have any comments or thoughts on some of his writings on that subject?
Dennis.
Since I'm the fusion guy, I probably get to answer that. No, I mean, so helium-3 deuterium is actually one of the fusion reactions which is considered. We actually use helium-3 in our experiments at MIT, but it's roughly 100 times harder than the standard kind of fusion, deuterium-tritium fusion. So that is in the future, because we don't have the technology right now, even with these new magnets, would not actually get us there yet, even with D-helium-3. But luckily we have another fuel source, which is tritium.
Question over here?
Well, I got a question, and I happen to have a microphone, so I'll try and go next. So if I understand you guys correctly, and this is what I sort of in the lines heard before, is that if we do space exploration, deep space exploration in the long run, we're not going to get around using nuclear power.
That's right.
What I'm still a little bit confused at is in which cases we are actually right now allowed to use it, like radiothermal generators are in space already, right? It's a sort of a simple form of a reactor, I guess. And you mentioned, right, there's space treaties that prohibit that right now. And so my question of these two sort of understandings combined is there a strategy forward of actually being allowed to use one of these in space? I mean, it sounds like the technology is not the problem. It's more like, how do we actually get to a launch that allows us to test and use one of these? Is there a strategy for that?
Yeah. You guys want to?
Oh, well, yes, but I'll just talk about, I think the technology might be more limiting than the policy. I mean, the policy we haven't really tested, right? We have launched the plutonium systems. One of our big problems, we're running out of plutonium-238 for the RTGs, and there's a program to make more of it, but it's only going to get you hundreds of watts. A decade is about the level we're taking, so that's not going to do much. But last times we've tried, we've been able to launch them. So the policy part's important. Right now, I think the current administration is very positive we can get a lot through, but it'll depend which way things go.
So I would say, you may be aware or you may not, that there has been the nuclear launch approval process has been modified, or is in a process of being modified. Everything in the past required presidential approval, everything, even the radioisotope. The new process, it's become more probabilistic in terms of the risk, in terms of how you assess it, and based on that risk, it breaks down who can approve it. So I think there's 3 levels now. There is the one that requires presidential approval, then there's going to be one that actually can be decided by the administrator of NASA. So the whole point of saying that is that there's a positive movement toward making
getting nuclear systems into space more realistic, right? We're not there yet. This is just one step of many, I think, that will have to be taken to get to the point we can launch those systems. But it is a policy question. Policies can be changed. I would say that.
Okay. Any other questions? Yes?
Is anyone looking at alternative fission fuels like thorium? Because you guys are looking way far out there, and so it's kind of a neat opportunity.
Yeah, you can talk about how good that eventually is, but the problem is that's going to make your mass like 10 times heavier to try to use anything that's breathable or that you don't take all your juice with you. You can make it as you go. But it's a great long-term solution.
So this is one of the things that we've looked at, because the other way to help combat this problem in what are called thermal nuclear systems is you use a neutron generator at the center. That's actually what we had in ours as well too. So yeah, it actually is. It's got technical challenges, but it's one of the ones which is interesting. Perhaps, although I have no idea about where it sits in laws, because if you're putting up thorium or depleted uranium, you're not technically putting fissile material on a rocket and putting it into low Earth orbit. So does that trigger the same kinds of conditions and concerns as putting fissile material? I'm not sure what the answer is, but technically they're extremely different from each other, of course. Yeah. And there's thorium on Mars, by the way, which is an interesting fuel source.
Okay, I think we're about done, and I just wanted to close with a word of thanks to our panel. Great insights, and there's a lot out there to work on, and we got a lot of work to do in the next 50 years to get us to Mars. Thank you very much.
Okay, great. Hello, yeah, good. Great session. Haitham, Brad, Dennis, David, Ron, Steve, thank you. Thank you, sir. Lots of great questions, and we better get out of here. Oh, exit that way. Let's go to dinner.